This screencast is going to build on the previous screencast on joint probability distributions and marginal probability distributions. We're going to be talking about conditional probability distributions in this screencast. I'm going to start with the same example that I did in the joint probability distribution screencasts. We've got some data here for whether or not there was snow overnight and whether or not the bus was delayed as a result. We have a total of 60 samples. If we divide each of those numbers in this table by 60, that gives us the joint probability distribution, fxy, of x and y, and that's covered in the previous screencast. Now we're going to talk about conditional probability distributions. We already discussed this a little bit when we talked about conditional probabilities. So to review, I want you to answer these two questions. We can determine the probability of A given B. Given that B has occurred, that means the bus is delayed. We have a event A, snow overnight, has occurred 5 of those 14 times, and that equals 0.36. Incidentally, that's the same as if we take our joint probability distribution here on the right, and we divide 0.083 divided by the sum of the probabilities of event B. So that's the same exact thing. The conditional probability that B occurs, given that A has occurred, A is snow overnight. So given that there's been snow overnight, what's the probability that the bus is delayed? And that's just 5 over 15, which is 1/3. And you can also get the same thing by taking 0.083 and dividing by 0.083 plus 0.167. This is kind of the foundation for conditional probability distributions. In the previous screencast, I showed this example. We had a joint probability distribution for these discrete events. X was the number of improperly tightened bolts, Y was the number of defective welds. And taken together, this table of data represents the joint probability distribution for these discrete variables. So I have a question for you that's related to what I talked about earlier with the snow and the delayed buses. If x equals 1, what is the probability that y equals 0? To answer this question, it's a conditional statement. If x equals 1, we're constraining ourselves to this column here. If that's the case, what's the probability that y equals 0? We can take our total probability that x equals 1, that's 0.045, and we divide 0.03, that's the probability that y equals 0, by that total probability that x equals 1, and we get 0.67. So this is actually a conditional probability. We denote this by f sub y when x equals 1. So this is the conditional probability of y. Y here equals 0. That's how we denote this. If x equals 1, the probability that y is going to be 0 is known as the conditional probability, and that's 0.67. We can refer to this entire column as f sub y given that x equals 1 as a function of y. And this in itself is composed of 3 elements. We have when y equals 0, when y equals 1, and when y equals 2. So this table here represents the conditional probability of y given that x equals 1 as a function of y. Let's try to come up with a general formula for computing this conditional probability. The probability that y equals any value of y and x, our random variable x, equals any value little x. What we did in the previous slide is we took 0.03, that's fxy of x comma y, that's the joint probability function when x equals 1 and when y equals 0, and we divided fx of 1. Fx of 1 is the sum over all y's for when x equals 1, and that's 0.045. And when we did that, we came up with the following computation, and that was 0.67. Again, this probability that y equals 0, given that x equals 1, we write that as f sub y, given that x equals 1 as a function of 0. So our y value is 0. We can extend this to continuous variables. The notation is very similar. There are a couple differences. The probability that y is in some subset b, that's what this symbol means. This means that y is within some set b, given that x is equal to some value of x, is equal to the integral over all b, and this will become more clear in a moment through an example, of our conditional probability of y, given x. Let's revisit an example from a previous screencast. We had this uniform distribution, this joint distribution. Calcium level can vary between 8.5 and 10.5 mg per deciliter, cholesterol between 120 and 240. We found that the joint probability distribution function is just 1 over 240. It has no dependence on y nor x because it's a uniform distribution. We found that the marginal probability density function of x was 1/2, and that of y was 1 over 120. Using our definition of probability, we can integrate the marginal probability density of y over all y. For this example, we're interested in what's the probability that y is between 130 and 135, given that x equals 10. We can take what we know about conditional probability distributions. That's the joint probability distribution divided by the marginal probability density of x. We can substitute what we derived previously into that. And when we put this into the integral and we substitute x equals 10, we integrate from 130 to 135. 1 over 240 divided by 1/2 becomes 1 over 120. We multiply that by 5 because when we integrate a constant from 130 to 135, we get 5. And in the end, this ends up being 4.2%. Another way of looking at this is we can draw our joint probability density function of x and y. And again, we saw that that was 1 over 240 for all values of x and y in this domain. X went from 8.5 to 10.5. Y went from 120 to 240. What we're saying here is that given that x equals 10, so we're constraining ourselves to this chunk of this joint probability density function. So we're constraining ourselves to this little slice. And if I bring this slice outside, so this is our fy given x equals 10 as a function of y, and this is y-axis. Now we're saying what's the probability that y is between 130 and 135. So we're essentially taking that little slice and dividing by the entire slice when x equals 10, and that's how we do this. This slice here, because this distance is 1 over 240, the total area of this big rectangle is 120 to 240, which is 120. So 120 times 1 over 240, that's the area of the outside rectangle. That's going to be on the denominator of our probability, and then the area of the shaded region is 5 over 240. And so what happens is the 240s cancel, and we end up with 5 over 120, and that's equal to 0.042. So that's how you can determine these conditional probabilities. Thanks for watching.